While we hopefully understand the basics of forces and how they make objects move, how do we measure and quantify an object's energy? Before looking at different types of energy, one other quantity we need to learn about first is work. This scalar quantity represents a force applied on an object over some displacement, and has a value of the displacement times the force component that's parallel to this displacement. One way to mathematically say this is the force times displacement times cosine theta, where theta is the angle between the force and displacement vectors. Graphically, work is the area under a force as a function of position graph. In addition, work can either be positive or negative, depending on whether the parallel force component and displacement vectors are in the same or opposite directions. With that, we can start looking at energy, which is another scalar quantity defined as the capacity to do work. In essence, work done on an object can increase or decrease the energy of that object, while an object's energy can be translated into work. Unlike work, however, there are many different equations and types of energies, so let's run through a couple of the most common ones, though these equations will all be on your AP equation sheet. The energy associated with an object's motion is known as kinetic energy, and has an equation of 1/2 times the mass times velocity squared. In other words, the faster and more massive the object is, the more kinetic energy it has. Another common type of energy is known as gravitational potential energy, which is defined as the mass times gravity times the height of the object, which is based on a height equals 0 level that you can choose conveniently for whatever problem you're solving. In addition, an object attached to a stretched or compressed spring has a spring or elastic potential energy equal to 1/2 times the spring constant times the displacement from equilibrium squared, which is based off of Hooke's law from my force properties and types video. For those of you that have learned circular motion and rotational kinematics, an object that rotates has a rotational kinetic energy equal to 1/2 times the moment of inertia times the angular velocity squared, a quantity that is separate from the translational kinetic energy. Finally, for those of you who know Newton's universal law of gravitation, two objects like the Earth and the Sun have a potential energy equal to the negative of the gravitational constant times the two masses, all divided by their separation distance, r. To measure an object's total energy, simply add together all types of energies the object has using the equations we just showed. For example, take this tennis ball thrown off the side of a building. Since it's moving, it would have kinetic energy. In addition, if we took the 0 height level to be the ground, it would have a gravitational potential energy in the air as well. Also, if it were, say, rotating, it could have a rotational kinetic energy. So keep adding the scalar energy types based on what the object is doing or where it's located. Lastly, one extremely important idea when it comes to energy is the law of conservation of energy. Essentially, this law states that the total energy on any system, or an object or collection of objects, must remain constant as long as there is no work done by external forces. For me, I like to think of this law in terms of snapshots. If you take any two instants in time of an object's motion and there were no external forces doing work during these times, say a block sliding down a frictionless ramp for example, then the total energy of that object must be the same before and after. The values of each type of energy, say kinetic and gravitational potential, can change, but their total sum must always sum to the same value before and after, leading you to useful energy equations. However, if the object at two different points did experience a force doing work on it, say a block being pushed by a person across the frictionless floor, then the object can gain different types of energy. You can even still write energy equations with these situations by simply adding the work done on the object into your equation to represent the object's change in energy. With that, you can feel good that you just finished learning about the basics of work and energy.